Hello everyone, in this video lecture we are going to analyze indeterminate frame by stiffness matrix method. So for this, consider this example. We know so frames are generally classified into two kinds. Okay, so one is a sway frame, another one is non-sway frame. Sway frame means the lateral displacement at the floor level or parameter means that is called as a sway frame. If the lateral displacements are restrained in this frame means it is called as non-sway frame. Okay, so sway, when will occur as sway means anything leads to unsymmetry means it leads to sway. Okay, so in our case loading also unsymmetry, then length of the column also unsymmetrical in nature. Okay, so therefore it is a sway frame. Okay, so first, so we know it is a stiffness method. Okay, stiffness method or a displacement method. So in this method, so first thing we need to determine is a degree of freedom. Okay, so for this structure how many degree of freedoms are available? So consider joint A. Okay, for this consider first joint A. So it is a fixed end. So at the fixed end degree of freedom is equal to 0. Then at the joint B, so it is a rigid joint, it is an intermediate joint, it is a junction of beam and column. We have one rotation as an unknown. Okay, one rotation as unknown, that is a 1 degree of freedom is available at the joint B. Then joint C also we have 1 degree of freedom, theta C. Then at a joint D, it is again fixed end, degree of freedom is equal to 0. Okay, so I already said it is a sway frame. Sway frame means it permits a lateral displacement at the floor level or beam level. So therefore you get one sway displacement delta at this beam level, B and C level. So therefore the degree of freedom or kinematic indeterminacy is equal to 3. So they are sway, then theta B and theta C. So this is our first step. We completed our first step. So what is our second step? Our second step is we need to assign one coordinate for each displacement direction. Okay, we need to assign one coordinate for each displacement direction. So for this we know degree of freedom is equal to 3. So they are, one is a horizontal translation. So for a corresponding coordinate will be force coordinate. So displacement means we concentrate force, rotation means you apply one moment coordinate. Okay, so our case, so in this structure this frame subjected to sway, so therefore assign coordinate 1 as a force coordinate at the floor level, BC level. So this is 1. Then second degree of freedom is a rotation. Okay, so theta B, rotation of joint B. So therefore assign second coordinate is a moment coordinate, so it is in clockwise direction. Then third degree of freedom is theta C, again it is a clockwise moment. So assign coordinate, third coordinate in clockwise moment. Okay, so this is 1, this is 2 and this is 3. Okay, then third step. Okay, so third step we are determining the final force acting on this assigned coordinate direction. Okay, so we need to determine this final force at the assigned coordinate direction. So what are our assigned coordinate direction? So first one is force first one is force coordinate and second and 3 are moment coordinate. Okay, so in this structure and this external structure, in this structure, so is there any force at a assigned coordinate direction 1? Yeah, we have one force, the 50 kN force. So its direction on the same as that of our assigned coordinate. So our assigned coordinate, it acts towards right. Okay, so it is a force coordinate, it acts towards the right. So this external force also at this joint B, we have one external force, that is 50 kN, acts towards right. So therefore the final force at the first assigned coordinate direction, that is P1 is equal to 50. Then is there any force or moment at a second assigned coordinate direction? So our second assigned coordinate direction is a moment coordinates. Okay, so is there any external moment at a joint B? No, there is no external moment in this structure at a joint B. So therefore this external, the final force is equal to 0. Then and joint C also it is a moment coordinate. So at this joint C also there is no external moment. Okay, so therefore P3 also 0. Okay, so therefore these three are represented as a column matrix. So it is P is equal to 50 0 0 50 0 0. So this represents the final force acting at the our assigned coordinates. Okay, so we completed the third step. Then what is our fourth step? So fourth step we need to restrain all the nodes, okay, all the joints, we need to restrain all the joints, that is we are resisting displacement. Then determine a force developed in the each assigned coordinate direction, okay. So in our case 3 assigned coordinate direction 1 2 3. So one is a force coordinate at a floor level, okay, at the floor level, that is BC level. Then second one is a moment coordinate at the joint B. Then third one is moment coordinate at the joint C, okay. So in this case in the fourth step we are restraining all the nodes, that is we are assuming all the ends are fixed end, okay. So we are assuming all the ends are fixed end, okay. So first consider this AB portion, okay. So this is AB, it is a column, okay. So column whose both the ends are fixed, A end and B end are fixed. So in this column there is no external force, means its end moments MFAB and MFBA, MFAB and MFBA both are equal to 0, okay. So there is no external force in the AB portion, so therefore its end moment 0, its reactions, horizontal reaction is equal to 0 at the both end, horizontal reaction 0, then vertical reaction is equal to 0, okay. So horizontal reaction is equal to 0, okay, moment 0, horizontal reaction is equal to 0. Our aim, our need is only this horizontal reaction and moment, so therefore this horizontal reaction is 0 and moment also 0. Then consider BC portion. So again consider end B and C are fixed, so it is subject to some uniformly distributed load 30 kN/meter, its length some 4 meter. So therefore its end moment M of BC equal to minus WL square by 12. Then M of CB is equal to, it's also WL square by 12. Okay, so it is a fixed beam subject to uniformly distributed load mean it is the end moments, both the ends moments are WL square by 12, but left hand subject to anti-clockwise movement, right hand subject to clockwise movement. Okay, so again in this case on the horizontal reaction is 0. Okay, so for a beam there is no horizontal force means horizontal reaction is also 0. Then consider CD column. Okay, again consider both the ends are fixed. Okay, so in this case also there is no external force, so therefore its end moment, both the end moment M of CD and M of DC both are equal to 0. Then horizontal reaction also 0, so there is no horizontal force, therefore horizontal reaction also 0. Okay, so in the fourth step what we are done means, what you are doing means we are restraining the structure. Okay, so we are not permitting any displacement at any node. Okay, so we are restraining the structure. So due to that restraining, what is the moment and force induced in the assigned coordinate direction? So what is our assigned coordinate direction? The first one is the force coordinate. Okay, so it represents a force at the floor level B and C. Okay, so for this three portion AB, BC and CB, so there is no horizontal force. Okay, so all the system there is no horizontal force means this force developed in the assigned coordinate direction 1 is equal to 0. Okay, that is P1 dash force is equal to 0. Then P2 dash force represents a moment developed. So our second coordinate direction is the moment coordinate direction. So therefore it is a moment at joint B. So what is the moment at joint B? So joint B is a junction of two members. One is BA member, another one is BC member. So therefore its moment is MBA. P2 dash force is equal to MBA plus MBC. Okay, we know MBA is equal to 0, MBC is equal to, we get some value. Okay, so substitute this thing, you get some P2 force. P2 force is equal to minus WL square by 12. Okay, then P3 force. Okay, so our third assigned direction is as a moment, it is a rotation. So therefore we are applied moment at a joint C. Okay, so what is the moment induced at the joint C? So it is again this joint on the, it is a junction of two members, one is CB, another one is CD. So therefore its moment MCB and MCD. Okay, so put MCB is equal to WL square by 12, MCD is equal to 0, you get this end moment. Okay, the moment due to restraining structures, that is P dash value. Okay, so P dash value. Then what is the net moment? The final moment and moment due to restrained structure, which is equal to 50, 40, then minus 40. Okay, So put this is the moment due to n, this is the n moment. So this is moment force developed in a restraint structures. Okay, just minus it. Okay, so we know general equation, the final equation, displacement is equal to stiffness inverse, stiffness matrix inverse into final force matrix minus force developed in a restraint structures. Okay, so we determine the final force in the third step, then P dash value in the fourth step, just minus it, these two things. Okay, so its value on 50, 40 and minus 40. Then we need only this stiffness matrix. Okay, okay. So in the next step we are going to determine a stiffness matrix. Okay, so in this fifth step we are going to determine stiffness matrix. So first, so what is the order of the stiffness matrix? Okay, so order of the stiffness matrix is equal to number of degree of freedom. So in our case it is a 3 degree freedom. So therefore our order of the matrix, stiffness matrix, is equal to 3 by 3 square matrix, 3 by 3 square matrix. So element of the stiffness matrix are K11, K12, K13, then K21, K22, K23, then K31, K32, K33. So first we are going to determine first column of matrix. So for this we need to apply unit displacement in the first coordinate direction. All other coordinate directions are restrained. Okay, so we need to apply only unit displacement in the first assigned coordinate direction only. Okay, so other coordinate directions are restrained. Okay, so our first assigned coordinate direction is, it is a displacement, that is translation at the floor level. Okay, so this is our structure. So initially this is our portal frame. So this is our portal frame. Now we are permitting some unit displacement at this assigned coordinate direction 1. So this is our assigned coordinate direction. So at this joint B and joint C we are permitting some unit displacement. Okay, so due to that displacement the frame deflects this way. Okay, so its value is delta. Okay, so draw the free body diagram for AB portion means, so initially it is like this. So due to that unit displacement this joint B move to some B dash position. Okay, so it moved to some B dash position. So its value is equal to delta. That is our right hand somewhat moves in the horizontal direction. So therefore you get some n moment. Okay, so due to that translation you get some n moment. So in this n moment are anti-clockwise moment, its value 6 delta by L square. Both the n moment anti-clockwise, its value 6 delta by L square. Okay, so substitute delta is equal to 1 means you get 6 by L square. Okay, so n moments are 6 EI by L square, 6 EI by L square. Okay, so fixed end. Okay, then you should determine a reaction. Okay, so reaction at the ends, both the ends. Okay, so in this case there is no external force. So this n moment, net n moment, it creates anti-clockwise moment on this structure. So the reaction, it should be developed in a clockwise direction to resist this moment. Okay, so our reaction, this horizontal reaction may be developed in this way. Okay, so one reaction then another reaction, so it creates clockwise. The net n moment on it creates anti-clockwise moment. So its value 6 plus 6 12 EI by L square. Okay, then this reaction VA and HA and HB is equal to net moment induced by n moment, that is 12 EI by L square divided by distance between these two end. Okay, so this is L. Okay, so finally you get HA and HB is equal to 12 EI by L cube. Then likewise draw the free body diagram for BC. Okay, so BC, so initially, so this is B joint, this is C joint, then we are permitting unit displacement at a joint B and joint C. So therefore its final position may be this. Okay, so in this case on the this beam, it is not subject to any transverse displacement. So therefore there is no n moment. Okay, so there is no n moment. So if n moments are 0 means all the reactions are 0, both horizontal and vertical reaction and moment reaction all are 0 for this beam portion. Then consider CD portion. So, this is D, this is C initially, then we are permitting some unit displacement. Okay. So, therefore, C move to some C dash position. Okay. So, due to that movement you get an end moment of again 6 EI delta by L square, 6 EI delta by L square, 6 EI delta by L square. Okay. So, put delta is equal to 1 na. So, both end moments 6 EI by L square, 6 EI by L square. Now, determine reactions. Now, determine a reaction, horizontal reaction at this level. Okay. So, now our case the net moments are developed in anti-clockwise direction. So, therefore, reaction is developed in clockwise direction. Okay. So, moment induced by the reaction only, it is developed in clockwise direction to resist this moment. Okay. In order to satisfy that equilibrium condition, so this reaction only should develop a clockwise moment. So, its value is equal to net moment divided by span. Okay. So, 12 EI by L square divided by L. So, both HC and HD. Okay. So, therefore, it is also 12 EI by L cube. So, put length for this portion of B. Okay. So, you finally get the end moment, you get end moment. Okay. So, now write the first column of stiffness matrix. Okay. So, what is our first column of stiffness matrix? The first one is K11, then K21, K31. Okay. So, this is our first column. So, K11 means force developed in the first coordinate direction due to unit displacement given in first coordinate direction. Okay. So, what is our first coordinate direction? So, this is our first coordinate direction, it is the force coordinate direction. Okay. So, therefore, we need to determine, so what is the force developed at the floor level. So, therefore, K11 is equal to HB and HC, it is represented as HB and HC. Okay. K11 is equal to, it is the force developed at the floor level. Okay. So, at the floor level we have two force. So, one is HB, another one is HC, both are in plus x direction. Okay. So, our assigned coordinate also plus x direction. So, therefore, treat this as a positive one. Okay. So, therefore, it is 12 EI by 4 cube. So, it is a reaction HB reaction 12 EI by 4 cube, then HC reaction is equal to 12 EI by 2 cube. Okay. So, you finally get 1.685 EI. Then K21 means it is the force developed in the direction 2 due to unit displacement applied in the direction 1. Okay. So, what is our second coordinate direction? Is the moment direction at joint B. Okay. So, at the joint B. So, at the joint B there are two members are there, one is MBA, another one is MBC. Okay. So, add MBA and MBC moment, you get K21 value. So, K21 is equal to MBA plus MBC. Okay. So, what is the value of MBA? So, MBA is at a 6 EI by 4 square, it is in anti-clockwise direction, but our assigned coordinate is in a clockwise direction, but induced reaction, induced moment is anti-clockwise direction. So, therefore, put minus sign. So, minus 6 EI by 4 square. Then what is the MBC value? MBC, it is a 0 moment. Okay. For a beam portion, BC portion, so its end moments and end reactions all are 0. Okay. So, therefore, the K21 is equal to minus 6 EI by L square, that is 4 square, you get minus 0.375 EI. Then K31. So, K31 means force developed in the direction of third coordinate due to unit displacement given in first coordinate direction. Okay. So, what is our coordinate direction 3 means? It is a rotation at a joint C, that is a moment at a joint C. Okay. So, at the joint C we have one moment is there. So, this moment also anti-clockwise. Okay. At joint C, so it is a junction of two members. So, therefore, K31 is equal to MCB moment plus MCD moment. Okay. So, MCB moment is equal to 0. Okay. For beam portion there is no reaction. Okay. So, it is not subject to any reaction. So, therefore, its value is 0. Then MCD. So, MCD is 6 A delta by 2 square. Okay. But it is anti-clockwise moment, but our assigned coordinate direction is clockwise, therefore, put a minus sign for this. Okay. So, therefore, you get minus 6 EI by 2 square. Okay. So, you get minus 1.5 EI. The next, develop the second column of our stiffness matrix. For this, allow unit displacement, permit unit displacement in the second coordinate direction only. All other coordinate directions are restrained, only second coordinate direction we are permitting some unit rotation. Okay. So this represents, this figure represents the deflected shape. Okay. So this represents the deflected shape. We are permitting unit rotation at a node B, Okay. So this is our structure. We are permitting unit rotation at a node B. Okay. So therefore you get some n moment. Okay. So you get n moment. So what are the n moments? So first consider the free body diagram for AB. Okay. So the AB at joint B we are permitting one clockwise rotation. Okay. We are permitting one clockwise rotation at node B. Okay. So therefore this end is subjected to the moment, clockwise moment of 4 EI by L. So L is 4 meter, it is 4 EI by L. Then this end is subjected to 2 EI by L. Then what is the reaction developed at the joint HC? Okay. So HC reaction is equal to, so our net moment on the is in clockwise direction. So therefore these horizontal reactions should be developed in such a way that it should counteract this net moment. Okay. So this net moment is in clockwise direction. So therefore a horizontal reaction is developed in the anti-clockwise direction. Okay. So it develops anti-clockwise moment. Okay. So it develops anti-clockwise moment. Its reaction, this HB and HA is equal to net moment 4 EI by L, 4 EI by 4, then 2 EI by 4. You get 6 EI by 4. This is the net moment divided by distance between joint A and B. It is 4 meter. Okay. So you get 6 EI by 16. Okay. HA and HB 6 EI by 16. So it is in minus x direction. Okay. Then draw the free body diagram for BC portion. So this is BC. Okay. So we are permitting unit rotation at the joint B. Okay. So theta B is equal to 1. So therefore you get n moment 4 EI by L. Then this is 2 EI by L. Okay. So we need to determine only horizontal reaction. So in this system there is no horizontal force. Okay. If there is no horizontal force means you get horizontal reactions are 0. So in this case horizontal reactions are 0. So only you get a vertical reaction. Okay. So therefore it is 0. Then consider CD column. Okay. So this is C, this is D. Okay. We are not permitting any rotation at both the joints C and D. Okay. So therefore n moments are 0, n moments 0, horizontal reaction 0, vertical reaction 0, all are 0. Okay. So now write the stiffness values. Okay. So what is K 12? So K 12 means what it represents? It represents the force developed in the first direction, due to unit displacement given in second coordinate direction. Okay. So what is our first coordinate direction? First coordinate direction, this is our first coordinate direction, that is the force direction at a joint B. Okay. So at joint B and joint C, it is at the floor level. Okay. So at the floor level what we get, the horizontal reaction. Okay. So we are getting only one horizontal reaction. Okay. So the free body diagram for AB column you get one horizontal reaction in this minus x direction, its value 6 EI by L square. Okay. So 6 EI by 16. Okay. You get 6 EI by 16, 6 EI by 16. Okay. But in this direction on the opposite to our assigned coordinate direction. So therefore our K21 is equal to minus 6 EI by 16. Okay. So you finally get minus 0.375 EI. Then K22. So what is K22? So K22 means force developed in the second coordinate direction due to unit displacement given in the second coordinate direction. Okay. So what is our second coordinate? It is a moment coordinate at the joint B. Okay. So moment coordinate at joint B. At joint B we have two members, one is BA and BC. So therefore K22 is equal to MBA plus MBC. Okay. So we already determined with the alpha free body diagram, you determine MBA moment is equal to, so what is its moment? Its moment is 4 EI by 4. Okay. 4 EI by 4. Then MBC moment also, it is 4 EI by, I think its length of the beam 4 EI by 4. Therefore K22 is equal to 4 EI by 4 plus 4 EI by 4, you get 2 EI. what is K3 K23 sorry K32 sorry K32. So, we are discussing second column of the matrix. Okay. So, K32, that is a force developed in the third coordinate direction due to unit displacement given in second coordinate direction. Okay. So, what is our third coordinate direction? So, it is moment coordinate direction. Okay. So, what is the moment induced at this joint C, which is equal to, it is again it is a junction of two members, that is CB members, then CD, MCB plus MCD. Okay. So, what is the value of MCB? Its value 2 EI by L. MCD is equal to 0. Okay. So, therefore, you get EI by 2. K32 is equal to EI by 2. Then next develop third column of stiffness matrix. For this, you need to apply unit displacement in the third coordinate direction only. All other coordinate directions are restrained from okay, or restrained. Okay. So, now we are permitting unit displacement in the third coordinate direction. So, what is our third assigned coordinate direction? It is a moment coordinate direction or rotation coordinate direction at a joint C. Okay. So, therefore, we are permitting unit rotation at a joint C. Okay. So, its deflected shape is like this. Okay. So, its deflected shape like this. So, again draw the free body diagram for each portion, determine what is the horizontal reaction at the joint B, joint C, and moment at a joint B and joint C. This is our requirement. So, for this, so first consider AB. So, in this case on the both A and B are not subjected to any rotation or translation. So, therefore, n moments are 0. N moments are 0 means its horizontal reaction is also 0, then its vertical reaction is also 0. Okay. So, this is the free body diagram of AB portion. Then consider BC. So, this is B, this is C. Okay. So, in this case we are permitting unit rotation at a joint C. Okay. So, we are permitting unit clockwise rotation at a joint C. So, therefore, you get a n moment 4 EI by L, that is 4 meter at the joint C, and the joint B 2 EI by L 4 meter. Okay. So, in this case only you may get some vertical reaction, but this vertical reaction is not necessary. So, we need only horizontal reaction. So, this horizontal reaction is equal to 0, that is horizontal reaction developed at the floor level B and C. So, its value is 0. Okay. So, then consider free body diagram for CD column. Okay. So, in the D we are permitting one unit rotation. Okay. So, therefore, this end is subjected to some moment 4 EI by L, that is 2 meter, this is 2 EI by L. Okay. So, due to that n moment, so this portion of column, it may subjected to horizontal reaction. Okay. So, this net n moment is in clockwise direction. So, therefore, moment induced by horizontal reaction is in anti-clockwise direction. Okay. So, it is anti-clockwise direction, its value is equal to net moment divided by L. So, net moment 4 EI by 2 plus 2 EI by 2, totally 6 EI by 2 divided by length on the 2. Therefore, it is 6 EI by 4, 6 EI by 4, that is 1.5 EI, you get reactions 1.5 EA. Okay. So, it is in minus x direction. So, now write the third column of stiffness matrix, that is K 13. So, K13 means a force developed in the first coordinate direction due to unit displacement in the third coordinate direction. Okay. So, what is our first assigned coordinate direction? It is this is force coordinate direction. Okay. That is, it represents some horizontal force. Okay. So, with the help of this free body diagram, we determine horizontal reactions at a joint B. Okay. So, for AB free body diagram you get 0 horizontal reaction, then BC free body diagram again you get a 0 horizontal reaction, but CD portion you get one horizontal reaction. So, its value is 1.5 EI, it is in minus x direction. Okay. So, this reaction, okay, so HC reaction is equal to minus 1.5. Okay, so HCG reaction is 1.5 EA in minus x direction. Okay, so therefore K13 is equal to minus 1.5 EA. Why minus sign means our assigned coordinate direction is plus direction, okay, plus x direction, but induced reaction at this level is in minus x direction, its value 1.5 EA. Okay, so therefore you get a minus 1.5 EA. Then K23, K23. So K23 means the force developed in the assigned coordinate direction 2 due to unit displacement in the assigned coordinate direction 3. Okay, so what is our assigned coordinate direction 2? It is the moment coordinate direction at the joint B. Okay, so it's a joint B, again it is a interjunction of two members. Okay, so its value MBA plus MBC. Okay, so we know this MBA is equal to 0, then MBC. So what is the value of MBC? So MBC is equal to 2 EI by L. Okay, so that is EI, you get EI value. Then K33 is equal to a force developed in the third coordinate direction due to unit displacement in this same third coordinate direction. Okay, so this joint B, so our third coordinate direction is the moment coordinate direction, so therefore you get a moment. Okay, so what are the moment now? At the joint C we have two moment, MCB and MCD. Okay, what is the MCB moment? It is 4 EI by 4, 4 EI by 4. Then MCD is equal to 4 EI by 2. Okay, so therefore you get 3 EI. Okay, so finally write down the stiffness matrix. So stiffness matrix is equal to K11, K1, K21, K31, K12, K22, K32, then K13, K23, K33. Okay, substitute all the values. Okay, first column, second column, and third column, you get a stiffness matrix. Okay, then finally we need to determine displacements. Okay, so what are our displacements? One is delta, then another one is a rotation B, then another one is rotation C, which is equal to, that is delta matrix, displacement matrix is equal to stiffness inverse into final force matrix minus force in the restraint structure matrix. Okay, so force developed in the restraint structure. Okay, so substitute, we know stiffness matrix, then final force, then P dash value. So you finally get this delta matrix. Okay, so this delta matrix is one is delta, that is a sway force, sway displacement delta, then theta B and theta C. Okay, so after solving this you get final displacement delta. Okay, that is sway delta is equal to 35.556 divided by EI, then theta B is equal to 26.67 EI, then theta C is equal to 0. Okay, so after determining this displacement, now you use a general slope deflection equation. So with the help of this equation you may determine the end moments. Okay, so for this first write general slope deflection equation for AB portion. Okay, for the AB portion, so MAB is equal to M of AB, MAB is equal to M of AB plus 2 EI by L, 2 times theta A, then theta B, then minus 3 delta by L. Okay, so for this AB portion there is no external force, this M of AB is equal to 0, then A and is a fixed and its rotation is equal to 0. So theta B we already know, then this B support, it moves in the right direction. Okay, so horizontally in the right direction, so we have this delta value. Okay, substitute this theta B and delta, you get MAB moment, then also find MBA moment, then MBC, this is a B moment, is equal to again M of BC, then plus 2 EI by L, 2 times theta B, then theta C minus 3 delta by L. Okay, So, our case on the beam portion which is subjected to some external forces, therefore, you get some m of BC moment. Okay, so it is already we determined. Then substitute theta b, we know theta b, then theta c. Then for this beam there is no transverse displacement. Okay, that sway force it is considered for only columns. Okay, so only columns are subjected to some perpendicular displacement, some transverse displacement, but beam is not subjected to any transverse displacement. So therefore, this delta term in beam portion is equal to 0. Okay, so that delta we are determined that sway delta. Okay, so it is used, it is to be used in only column portion. Okay, so only columns are subject to transverse displacement. Therefore, in the general slope deflection equation, you substitute delta is equal to that 35.566 for AB and CD column. Okay, but not, it is not applicable for BC. Why it is? Because means at BC there is no transverse displacement. So therefore, its value delta is equal to 0. Finally, you get all the MAB, MBA, MBC, MCB and MDC. Then finally, draw the bending moment diagram. Okay, you guys already know about how to draw the shear force and bending moment diagram with the help of this end moment. So try to solve it. Okay, thank you.